And number 3, a 40-kilogram child is in a swing that is attached to ropes 2 meters long. Find the gravitational potential energy associated with the child relative to the child's lowest position under the following conditions. So the first part, when the ropes are horizontal. So before we get going, let's make sure we identify the things that we know. We know the mass of our object, the child, 40 kilograms, right? It's in a usable unit. We don't want to be using grams or anything other than kilograms because the units like newtons and things like that assume that you're using kilograms. So unless you standardize to a kilogram, you're going to be messing stuff up in your calculations towards the end. We have acceleration due to gravity, right? Because we're playing on a swing. And then we have, let's call it length of the rope, the swing rope. Coming in at 2 meters. So we're going to be using gravitational potential energy, and we do have a nifty little equation that we can use for gravitational potential energy. We know that potential energy is equal to mass times acceleration due to gravity, at least we're going vertical, multiplied by the height. Now again, potential energy, mass, measured in kilograms, like we said, acceleration due to gravity, and then h is going to be our height, the height of the child above the lowest position, okay, relative to the lowest position. So height above the lowest position. So let's get into this one. In case A, the ropes are horizontal. So when the ropes are completely horizontal, the child is going to be at its highest possible position, right? Because again, we'll draw it over here, swing. The ropes are horizontal, it's out this way. So that kid is up there, right? That's at the very, very highest position. It's going to be exactly 2 meters above the lowest point. How do I know that? The ropes are 2 meters long, so it's going to be hanging down 2 meters at its lowest point. And so up here is going to be kind of at that pivot point, and so there's going to be a 2 meter difference between these two. And so one of the things that I already know is that I can calculate the gravitational potential energy knowing that my height is 2 meters. Therefore, potential energy is equal to 40, sorry about my penmanship, 40 kilograms multiplied by acceleration due to gravity, multiplied by that length, that 2 meters. And so that is going to give me, if I just write it a little bit out of the way, how many sig figs do I need? I need 3, right? Okay, so I'm gonna round to right there. So I'm actually gonna report 785 joules as my answer for part A. Gravitational potential energy. All right, but B has another set of conditions, right? So we're still trying to calculate gravitational potential energy, but this time we're doing it in a different scenario. So here the ropes are at 30 degrees with regard to the vertical. So in this case, we need to find the new h, the new height of the child, above the lowest point. So the vertical height from the pivot, right, from the pivot is going to be given by just basic logic. It's not as though we've gone over this equation per se. So, well, I guess I used the lowercase, so I'll just go, sorry. Just to be consistent, that's the same thing as over here. So again, this is just logic. It's not like this is an equation to memorize. So you ask yourself, why am I using cosine here? Well, the length of the rope, which is L, forms the hypotenuse of a right triangle, where the adjacent side represents the vertical height. And again, we're looking for vertical height. We're trying to look for height above the lowest position. So the vertical height from the pivot of the child, from the pivot to the child. Using the cosine helps us get that adjacent side. So we multiply that cosine 30 by L that gives us the vertical distance from the pivot, and then we'll subtract that distance from the pivot. Yeah, we'll subtract that from our original value for L, and that's going to give us the height above the lowest point. So you might ask, how am I supposed to know I don't want to use sine? Well, sine is used, remember, to find the opposite side of a right triangle, in which in this case, it would give us the horizontal distance of the child from that original pivot, from our vertical axis. But we're looking for the vertical height above the lowest position, not the horizontal distance from this pivot. Right? So cosine is going to give us the vertical distance, the vertical portion of that triangle that's being made. So let's get into some of our substitutions. So this is going to end up being, see, that's 2, right? 2.00 meters. I'm going to subtract 2 meters cosine 30 degrees. So that means that h is 2 meters minus 2 meters times, my calculator tells me that cosine 30 is 0.866. So that means my value for h, my height above the lowest point, is going to be 0.268 meters. Now that we have that value for h, we can go back to our original equation for potential energy, and we're ready to plug and chug. This is still 40 kilograms. We're still rocking with the same gravity. And then I just determined my value for h. And so I come up with, how many sig figs? I still want 3. Still want 3 sig figs, right? 3, 3, 3. I didn't do any. Yep, we're still good there. So let's go round that to 105 joules. And then we'll do our last scenario. Part C, we have at the bottom of the circular arc, right? So at the very bottom of this circular arc as the swing goes, at the very, very bottom. So at the lowest position, the height above the lowest point is 0, right? At the lowest position, there's no difference between that and the lowest position, okay? And so h in this case, h is going to be 0. So what happens when I go to plug in 0 for that h? It's going to make the entire term 0. Now, if I want to be super snarky, maybe I'll throw in some significant figures, but there's no gravitational potential energy. Again, which makes common sense because this is a swing. If we define the bottom portion of this swing to be the 0 portion, or sorry, the 0 point, the child has no capacity to fall any further than this point on the swing. So this is the 0 point. And so if the seat of the swing is at this location, at this level, there is no more capacity or potential to move in the vertical direction. Now, again, you might be snarky and be like, well, what if the swing breaks? No. We're talking about this swing here. We're defining the system as this being the bottom point, this being the 0 point, and so we're not coming up with kind of like extra fun narrative reasons why we can change some of our assumptions. We do have to go along with the assumptions of the problem that we're solving. But we have 3 different situations, and we're using our triangle skills as well as our definitions of potential energy to make the calculations. One more time to make sure everything fits on the screen. And there we go.